This is 712, 713. All of this I'll call periodicity. I'm going to call this video part 1. I know there'll be more than one video of this. The good news is this is really easy. No math. It's more like factual information. The only thing bad is I'm probably not going to be able to tell you the assignments until the end of the lesson because I'm going to see how far we got and what I'm able to go over. So the worksheets, I actually copied them this time because it's going to be kind of easier for me to kind of look at that and go over it. But it looks like this is the first page. We'll probably do some of the first page in the first lesson, of course. And then the second page looks like this. All right? And then the third and fourth page we might or might not even get to. Now, if of course, like I always tell the bad news, not the bad news, but the AP students, you're probably going to have to watch, more than one of these section videos and do them, where they might do one in general, 30-minute one. You might have to watch 30 an hour and then do something, but do twice the work. But I'll try to make the work a little bit. This is so easy that I don't really need to cut down the work really for anybody. But that's always the case. I mean, I'll go through. All right, here we go. First of all, before I mention 712, well, I'll tell you a little bit about. I'm going to bring up something I want to bring up about periodicity, the periodic law. Now, this is a good place for me to throw in something that it's something advanced you need to, for AP really, but anybody can know about this. Well, first of all, there are a couple of elements. We're going to look at all the elements, the electron configurations of all the elements in the periodic table. And when we do that, you'll see that the periodic chart is the shape and the arrangement is based on that. Now, we already told you that. But I once told you that if you follow the little pattern, you draw a little arrow up, 1s2, 2s2, 2p6, 3s2, 4s2, 3d10, etc., on up. If you do that and you go in order, you'll get most of the electron configurations correct for most elements. But there's a lot of exceptions. Now, the exceptions mainly have to do with what is more stable for the atom. So here's one thing really for AP, but for anybody. If you ever hear like a question like, well, why is this electron configuration different than what we normally expect from others? It usually is because of what I told you called the Aufbau principle. Aufbau, which just says that building up, that as electrons are added to an atom, just pretend that they're empty, Hog Hotel's empty, you add 1s1, 1s2, 2s1, 2s2. As electrons are added, each electron will always be in the position, the orbital, that results in the lowest overall potential energy for the atom. Having low potential energy means the most stable. So it's always the most stable arrangement. It's what we mean. Like I told you, if these are not magnets. I don't have them with me, but but if this was like north, south, magnets would attract opposite. The north of one would attract to the south of the other. This would not be stable. I could force those together, but that was not stable. So they might be even like floating one above the other like that, okay? And if they would just move over to the side. Or a table would be even better. If I push them together, the magnets opposites, or the other opposites ends, they would, if these were magnets again, north, south, that would repel and that would repel. You could hold them there, but as soon as you let go, one's going to move over. And you can kind of move one along like that too. So it's not stable to be like this, but like this. That's how it is in the atom. Sometimes the electrons build up so much that it's just more stable for it to jump up to a higher room. But now, as that room gets to be more and more full, then what's more stable for the next electron? If this room becomes full, then it's like, well, the next electron now they're going to go on up, and now they're going to go and fill those other levels. I don't know if that might have sounded very abstract. I talked about this in the earlier video. I'm getting off the subject a little bit. Well, okay, so there's two important exceptions. Important exceptions in electron configuration. I want AP to be aware of this especially. Copper and chromium. Chromium and copper. Okay, so let's look at copper and chromium for a moment. So, copper, you would expect that copper is D9. That you say argon, 4s2, 3d9. That's what you expect. However, the real one is argon 4s1 3d10. Aha! So copper is 4s1. So the thing is, if an element has a chance, it would rather have a half full D system or a completely full D system. There's something more stable about that. So we talked about it. Now again, it has to do with which atom you have and all. Not all the atoms do this. Copper and chromium do it. And I don't have the list with me, but let's see. I can remember. See, copper, chromium. But like molybdenum might also do it. But anyway, that's the main ones we'll just look at for now. Copper and chromium do that. Well, chromium are different. So one electron that was in the 4s actually goes into the 3d. So it starts off like, let's just say the element before copper. Which one is that? That is nickel. Nickel would be 4s2 3d8. But then when this goes up to 3d, what you would think it's going to be 3d9. Okay. But instead of that, it pulls an electron from the 4s over into here to make it 4d10. So that's actually copper's electron configuration. It's better to have that full D system. Remember, every atom would like to have all the floors full in order, 1, 2, 3, 4. So in this case, it fills up that one. All right, the other one is chromium. Now chromium is, you'd expect it to be kind of the same deal. Argon, 4s2, then 3d1, 2, 3, 4, 3d4. Argon 4s2, 3d4. But what happens is, you can see, if it can be half full, the electrons 4s. I guess I could have done it this way also with copper. This might be a good way to show it if you had to ever see it on an essay question. But what will happen is, chromium will not be that. The electron that would have been 4s2 will move over here. And this actually makes the most sense of the two. Because look, now everybody has their own room. So you might think, well, why doesn't copper do something like that too? Well, copper does move. Yeah, copper moves one over and they're full. It has to do with with the nucleus. And remember, the nuclear charge of copper is a lot stronger. So copper is like this, but it's able to hold in all the Ds. 2, 2, 2, 2, 2, 10 electrons in the Ds. Chromium doesn't have quite as strong of a nucleus, but it is more stable for the atom to have single fill all of them than to have one electron here and these be single fill. So remember, there is some repulsion between those. Only if they were moving perfectly one clockwise and one spinning counterclockwise. Remember, one clockwise, one counterclockwise. Only then perfectly would they stay like this. But so this prevents all of their interference with each other, all the repulsion. Okay, I'm sorry that I threw that and tacked that on at the beginning of the periodicity lesson, but I didn't know where else to put it. And so, okay. So now, I might can cut that video section out, but I don't know if I will and put it separate. I probably won't. All right, periodicity. So here it goes. So after Erwin Schrödinger had the wave equation, and after the scientists figured out this whole thing about, let's call it 1s, 1s, then 2s, 2p, 3s, 3p, 4s. After all that was decided, all electron configuration, S, P, D, F, S2, P can hold 6, D can hold 10, S can hold 14. Well, it's amazing that after that was done, the scientists mapped out all the electrons and said, well, okay, if that's true, if the Hogg Hotel is true, let's see where all the elements will be. Now, keep in mind that these elements were not arranged this way. Okay, this chart did not exist like that. It was like more like a big square chart with all the elements in a row, pretty much by their weight. And that almost gives you the same order, but he didn't have this strange little shape and all that, so they wouldn't be. Well, anyway, when they put them in the Hogg Hotel that way, they noticed something. They noticed that whenever elements have the same, the same valence electron configuration, or the same outer shell configuration, they have the same properties. That's amazing. So that's actually what the periodic law says. And I'll do a few of these and show you. You already kind of know this, but I'll show that to you. I've already told you that, like, starting with hydrogen is 1s1. Okay? Then below it, you have lithium, which is 2s1. Now, you could technically say, okay, hydrogen is, the block is 1s1. All right. Then the next one, I'd have to say the short form would be helium. Then I'd put in 2s1. Or I'd put in neon, and I'd put in 3s1. Okay, then I put in what, argon, and let's see, argon and 4s1. So this kind of gets you from, all right, so what this is telling you, this is hydrogen. Maybe I'll use another color. I'm kind of squeeze it in there a little bit. But this one is hydrogen. This one is lithium. This one is sodium. And this one would be potassium. What a mess I'm making on the board there. I'm sorry. I'll just take away that noble gas for a minute. That'll be easier. H, lithium, sodium, potassium. And you already know that from the block location. Okay, well, here's the deal. So the idea is, in their valence, they only have one valence electron. I guess I should have written the same thing, but like that. If you want to put helium and neon and argon. So I'm just trying to write the short form electron configuration. Well, let's jump all the way over. Okay, so that's hydrogen. Then in the next column, there is nothing next to hydrogen, but we have beryllium, magnesium, and calcium. So beryllium is, well, okay, I guess I can write it. I'll just do it this way. Beryllium, sorry, it's here. Magnesium, calcium. I'll just do those two. And it goes 2s2, 3s2, sorry, and 4s2. Kind of a mess there, isn't it? I'm just trying to show you the first two groups. So group 1, I'll just take that one off too. Group 1, group 2. Okay? 1s2, 2s2, 2s1. I'm sorry. 1s1, 2s1, 3s1, 4s1. Then that's 2s2, 3s2, 4s2. You already know this. Okay, now let's jump over to the other side. If we go all the way down to group 8, the noble gases, let's see how they look. Let's mainly start with the neon. All right, let's look at neon. Well, I guess I should put them about right there. And then below neon, argon. And then below argon, krypton. So neon is just like helium, but then it's 2s2, 2p6. Argon is just like neon with 3s2, 3p6. And then krypton is just like argon, with 4s2, 3d10, 4p6. Now, can you remember I told you back some lessons backwards from here, that 3d10, even though that's part of the short form electron configuration of krypton, we don't count those as valence electrons. Why do we not count them? Well, we don't count them because they don't come out. See, the only thing good about being a valence electron is you're able to leave the atom and go bond with another atom, help in a bonding with another atom. So valence electrons of one atom and valence of another, they're shared, as we'll talk about in the next chapter in bonding. Those valence electrons are shared to make a bond. Well, if you have a 3d10, those electrons are not available to share. They all belong just to the atom of krypton, 3d10. But the 4s2 and the 4p6 do. Well, the point is, I don't know if you can see it so well, I have to blow it up on the screen there, but all of these have 8 electrons in the valence. 6 plus 2 is 8, 6 plus 2 is 8, 6 plus 2 is 8. All of group 1 has 1 valence. All of group 2 has 2 valence. Okay, I left off my little 2 there, didn't I, also? All right, and if I go before group 18, I said group 8. I'm sorry about that. Group 18 is the official number. It is called group 8 in some systems, but not the one that we're using here. Group 17 is going to be like fluorine, chlorine. Well, helium will be up here also, by the way. I didn't put helium. It's just going to be 2s2. 1s2, sorry. Now, but here's something interesting. Okay, I'll tell you that in a second. And so all of these are just going to have 1 electron less. Like if you get down to, let's see, click on the chart, fluorine, chlorine, bromine, and iodine. So fluorine, chlorine, bromine, what fluorine would be here. Fluorine, chlorine, and bromine. We didn't do all of these. So fluorine, chlorine, bromine, that's going to be 2s2, 2p5, 3s2, 3p5, and 4s2, 3d10, 4p5. Oh well. Sorry, I'm trying to fit this on here. This is a good thing to use with a giant chalkboard that's really wide to try to put them all on it. What I'm trying to do is write real small and squeeze it. And on my chalkboard, it kind of works better when we have a bigger one in class. I can really spread this out. But the point is, you could do all of them, but this will probably be enough to get the idea. Okay, so what's the deal with this? So the scientists, when they made the periodic table, they decided to put it in this order. Somewhere when electron configuration was formed, after electron configuration was formed, they decided, let's put everything with S1 in this column, and we'll make the shape so that as you go through one period, remember the period of the horizontal rows. If I go through one period of elements, the first one would just be hydrogen and helium. Then the second period, then the third period, and then the fourth period. I guess something like that. Okay, so first, second, third, fourth. If you arrange them this way by their outer electrons so that every group has the same number of outer electrons, that's why you have this weird shape like that, and this, and that, and so forth. If you arrange them that way, then you'll find that their chemical properties recur. They recur. All right, say periodically is a word for that. Now, I'll talk about that in a minute. So, but here's the deal. Everything in group 1 has one electron in the valence. You know they all form a positive 1 charge because all of these elements can lose one electron. And when they lose an electron, as I mentioned in an earlier video, they become isoelectronic with a noble gas before it. You know, in the chart, if lithium loses one electron, then it will become just like helium. Okay? If sodium loses one electron, it will become, electron configuration will become like neon. Potassium loses one, it becomes like argon. Okay? Fluorine, on the other hand, needs to gain one, it will become like neon. That's why it forms a -1 charge. Because fluorine has to gain one electron. 2p5 comes to 2p6. Chlorine gains one, and bromine gains one. This is telling you why every element forms a -1 in this chart, in this column, because they have to gain one more. What's the big deal about being like a noble gas? Well, as we said, the noble gases do not react. They're like stable, inert is a word for that. Inert, non-reactive. So they don't form bonds. They're safe. They're low potential energy. A lot of teachers want to say they're happy, but they don't like that word at all in AP for sure. They're happy now because everything is stable. It's like all your positive nuclear charge, nuclear warmth of the fire, and all the negative electrons have this perfect union, this perfect ratio of everything is just spread out great. No extra negative, no extra positive. It's just great. Everything's distributed wonderfully. That's what a noble gas is like. Well, these can't be a perfect noble gas, but by adding an electron, a negative electron, it becomes pretty much non-reactive, okay? And it becomes, so F-1, Cl-1, Br-1. Table salt, when you eat salt, you're tasting, sodium +1 is in salt, okay? That's what you mainly taste. All right, the chlorine is Cl-1. Well, those two things are stable. In your mouth, they stay. When they dissolve, they're still Na+1 and Cl-1. They don't change to anything else. They're stable in that form. And that's what your body uses. Your body needs sodium and potassium, you know that. And I'm sure chloride probably has some place in your body, and biologically, I don't know where, but some chloride ions might do something. I don't know all of that too well. A AP bio teacher might know better, so hopefully would know better. All right, now, what else do I want to mention here? And then you could go backwards and continue on and say, okay, so everything in this group, oxygen or 2p4, they want to gain 2 electrons, and they would get -2 charge. They gain 2 to become like the next one over. Well, anyway, all right, so what's the bottom line of the periodic law? The periodic law says when electrons are arranged in this chart form, when electrons are arranged by electron configuration, the properties of elements recur periodically. All right, so that means whatever things that lithium does, lithium metal, you can expect that sodium will do the same thing, or potassium, or even hydrogen. Okay, it's probably better to keep just the metals in here because hydrogen's kind of on its own. But I'll talk about these. So, for example, if you take pure sodium metal, it's an alkaline. These are all called alkaline metals. You take them. If you drop a piece of sodium in water, it reacts. It catches on fire, explodes. If you do potassium, it does the same, but actually more violently. Rubidium more and more and more. I've told you about that before in the past lesson. Well, it's interesting. They do the same thing. They also have the same charge. They also make the water basic, a hydroxide. They also cause hydrogen gas to be given off when you drop all these in H2 gas. When they're dropped in water, these all produce H2 gas, except for H, of course. So what an amazing thing. They all do the same thing, and they have the same electron configuration. So when the scientists figured this out, electron configuration, they're like, wow, that's why all these metals act this way. Okay? Or how about this? That's why all these noble gases will not react, because they are because they have this full shell system. And that's why, helium, argon, these are all very similar. Okay, that's why all of, think about this chart, this group, fluorine, chlorine, bromine, iodine, they all form -1. They also all form F2, Cl2, Br2, I2. Now we'll talk about that, Hofbrinkel. In the next chapter, you'll see why they make it F2, Br2, Cl2. Why is that? Well, it has to do with electrons, again, and how the electrons bond one to another. So any element you pick on the chart, here's an amazing thing that I like to see, like go to copper. Look at the group copper is in. If I go down one period below, silver. One period below, gold. Isn't that amazing? Those are like three of the most valuable metals, mainly because they do not react. I mean, especially gold doesn't react. Silver reacts a little bit more, and copper reacts the most. But these three metals just happen to be in the same period because based on their electron configuration. Now, I showed you copper was a little different. I'm trying to think if gold or silver do that. I don't think it does, but I'll check back. But anyway, that's the main ones to look at. All right, now, so that's the periodic law that says the properties of an element will recur periodically. And a periodical, a newspaper is a periodical. A magazine is a periodical. An annual report is a periodical. So anything that comes out in periods, like every day, or once a week, or once a month, or bi-monthly, twice a month, or annually once a year. That's what we mean by period. So in every period of the chart, every cycle, you will find aluminum will be just like gallium, +3+3, just like indium, and so forth as you go on and on in the chart. That's all the periodic law says. Now, because of this, we have all those names of the groups, the alkali metals, alkaline earth metals, etc., and everything. Well, you know what? There's not a whole lot to say. No, I was going to tell you. This section, the periodic law, representative elements, transition first, transition second, third, fourth, inner transitions. And I mentioned alkaline metals. All of this you see on the chart. You've seen this in a past chapter. The alkaline earth metals, transuranium elements, and everything like that. So this really goes with the other lesson on that. It was on the quantum number worksheet. And it's one that everybody can do as a bonus if you wanted to. But anyway, you should know all of that stuff. So there's nothing to do right now in this one part. But the next part I'm going to tell you a little bit. I'm going to give you some assignment on that worksheet. So this first section kind of goes with that section on quantum numbers where it asks you to match. I don't think I have a sheet with me. Oh well. But it's on the bonus lesson. If you look at the bonus lesson, you'll see a section that tells me, is this an alkaline metal, an alkaline earth metal, a halogen, a noble gas, what periodic type, what's the atomic number, all that kind of stuff. So that is periodicity right there. Now, you're going to find out in the next videos that it's more than just what I told you, more than just charge -1 or Hofbrinkel being, F2, Cl2, Br2, I2 and all that. More than that, there are many other patterns and properties you can predict based on where things are in the chart.